Did you bring with you a large sledgehammer class?
Yeah, I did not.
To finish your costume.
It's like I had left at home. That's the thing about it. So
Too bad. You know, maybe the construction guys have one.
I could borrow one. Yeah. That's actually.
Wait, what?
Makerspace definitely has one. Just grab one.
They already ran out. I don't know how much I would stock.
Oh yeah.
For 2 hours. I'm
There's also bolt
broken.
cutters.
I'll never be the same.
So then
You don't want to be seen walking around.
yeah, grab construction pads.
Keep those in the stack.
I don't think they did that though. You think they do better? They're CS majors. They're not event. How can I find better in the entire department? I bet you
Read for yourself in your case looks like a game boy.
I do.
Or take a part of it.
I walked up there and I'm like,
My favorite part of working in the makerspace is when I just have my phone. I need to get.
and I was like,
That's not my backpack. Sorry.
Honestly, if you put up like, what's this print? Cases for Flipper Zero.
Fix your code, not the automated. It's not the automated. Is there a reason to have hard code that
there's actually
Is there a reason?
and she asked me like,
Why would you have hard code songs? Like, this is
I
bad.
got that. I'm pretty sure it was a large or a medium. And then she's like, no, I'm not a large. I'm just
Mine's
right?
Only code page.
Or that's like,
If you parse those code pages,
but I didn't know it was the yes, but
We're thinking about working on
let's look at it.
Owen.
I'll look at it.
Owen. What's going on over there?
Birthday?
Whose birthday?
CICS birthday?
Oh, wow.
The Department of Computer Science changed the name to College of Computer Science, and now the party for the name.
It's a department under College of Engineering, and now it says its own separate. Oh, it's CNS, sure. Well, I think also Ryan's stepping out of data, right? What?
Yeah.
She's getting awesome. Was this new guy Ken? What's his name? I don't know. I just some NPP. Oh, Keith Marzullo. Okay, class started already.
Good afternoon. Good afternoon, everybody. How are we doing? Has everyone finished the homework?
yes.
Thank you. The homework that we're going to give today is going to just be a report with your team on your final project, and I would like you to spend the 3 hours a week that you should be spending on the homework on your final project so that people can get caught up there or get started if they haven't gotten started yet. I will also be providing a user credit program for you to exploit. I had made it for the CTF, for the Cybersecurity Club, but I don't think anybody finished it there, so I'll use it as an extra credit here, and it will be worth one other homework. So if you totally face planted on homework 1 or homework 2, you have a chance.
Can we get partial? Like if we aren't able to complete it, we can get like partial away.
Yeah, sure. Yeah, you'll get, if you get EIP but you don't get execution, you will get partial credit. I don't know. Jade may or may not make the grader for it as her heart desires. If she doesn't, then it'll be you contact me with your solution and then I'll grade it and give you points. Other things about homework, we are getting kind of compressed as far as the homework timelines go, but I still want to give you a good heap overflow and a use after phrase. So what I think I'm going to do is I'm going to get those written up, and on the date on the syllabus that it says you're going to get homework 5, I'm going to give you 5 and 6 together, and then they'll both be due at the end. How does that sound? Would anybody be upset about getting their homework early and having it be due late? No? Sounds good? Awesome. Okay, cool. So we'll do that. And then if you find the use after free to be beyond your skills, you could do the other one, and that would count as well, right? So you could pick 2 of the last 3 homeworks to do and still get a full grade. Today we're going to take a small I'm going to fix my recorder. Okay, we're going to take a small detour from heaps. Our next lab is going to be the unlink, which I won't be giving as a homework because it takes a long time and is kind of convoluted and a little bit difficult to debug, but we'll walk through it together as a group. And today we'll do a little detour to process manipulation because you now possess all of the skills needed to perform process manipulation. You have looked at position-independent code, writing position-independent code when you write your shell code, right? You've looked at remapping page protections or mapping new pages in the last homework using mmap or mprotect page protections. You've looked at drop and bootstrapping execution with drop. And so that's everything that you need to understand to do process manipulation. So, question is, what is process manipulation and why would you want to do it? So when I say process manipulation, what I mean is making changes to how a program in flight is executing. So not changing the binary on the disk to make changes to the program, but making changes to a running program that is in process. So either hooking or thread injection or things of that nature. So what are some things that we could do with that? Why would we want to do this? The first one is post-exploitation work. So let's say you get a shell on a machine, and what you would like to do is backdoor one of the services. So let's say you would like to inject a thread into a Win login that will dump all of the keyboard entry for somebody who's typing on the main login screen on a computer. Or you've got a web server running and you want a secondary log of everything that's going through that web server to be sent to another computer off of the network. Yes?
Is this the kind of like a prerequisite to systems?
Not necessarily. A lot of C2 does not use process manipulation at all. So the question was, is this like a prerequisite for like command and control? And it's not. Usually, nowadays, all command and control is run through just a program that is hidden and running on the system, and it is speaking outward to an external server to either dump information out or get commands from external. For the most part, it's not done in this way. However, one thing that you could do if you, say, owned a web browser on someone's machine is never touch the rest of the machine and just live in the web browser perpetually, because most of what the person does is going through the web browser nowadays anyway. Funny thing, there is no way to lock a privilege token to a specific piece of hardware. So what I mean by that is you log into some service through a website with like a single sign-on, your multi-factor authentication, and you click the button that says, keep me logged in for 30 days. What happens is you get a cryptographic token, right? Someone can take that token and use it on another computer. And there's no way to stop someone from doing that, because when you own the computer, you own the computer. There's no way to tie it to hardware. Microsoft spent a lot of time trying to figure that out and never did. So if you just live in the web browser, you could just sweep up all those single sign-on tokens and move them elsewhere in the network and do whatever you like, right? And so in that scenario, you would use process manipulation. You would want to add your custom code in there. You would want to hook a function, and we'll talk about that in a second. Second use, fuzzing. Let's say we have a service target, and it's pretty time-consuming to connect a socket to that service and push our stuff over and then kill the socket, because the functions that we're trying to fuzz are kind of deep in there. And so that takes a lot of time and a lot of processing power, and it runs your electricity bill up. One thing that you might want to do is just test the function directly in the context of the program. So run the service and then inject a thread that is talking to your fuzzer that is just running those functions directly. So that's another thing that you could do there. Another use would be for defense. Most defense products look like a rootkit, right? In the scenario I discussed with web browsers where, oh hey look, the clock works again, that's nice. In the scenario with web browsers where I talked about monitoring what someone is doing and stealing that, taking it off to someplace else, that's what you want to do in a defense scenario. You want to monitor what a process is doing in certain contexts, and then dump that information off to another process, most of the time nowadays, not even on your network, in the cloud, for that to be processed to decide if something untoward is going on, right? So one of the products and pieces of functionality that I worked on at Cisco is doing essentially, let's say, a block list SE Linux. So what SE Linux does is it watches all of the syscalls that a program makes, and it's got a policy, and it says, this program is only allowed to make these specific syscalls, right? And if the program makes a different syscall, then the kernel kills it. And so this is what's running on a lot of the programs on any Android phones you might have. It's one of the most obnoxious parts of finishing off an end-to-end Android exploit is beating SE Linux, because it's actually really strong. The problem is a lot of people don't use it, and that is because you need to know exactly all of the syscalls your program might make, otherwise it's going to be killed. And people don't like to make those profiles. It's a lot of work, and you often get it wrong. And especially if you're looking at a web server and someone wants to add like some PHP nonsense to it, it's probably going to start doing other syscalls that aren't in your profile, and then you're going to have somebody who is knowledgeable enough to strace the thing and then write a new profile for SE Linux, and that is very expensive. So companies don't do it. So what we did is we monitored the syscalls, and we said, if I see these 5 syscalls doing this in this amount of time on this thread, then I know some sort of malicious activity is occurring. So let's say I'm talking about the token theft stuff on Windows. Windows token theft, it's been publicly called hot potato attacks for like a decade and a half. There have been like iterations on it. But if you are using the Windows syscalls to perform that action, it's a pretty set number of syscalls. You have to do it in this particular fashion. So I can watch a process and say, if I see the syscalls in that order, that's probably what's happening, and kill it, right? But in order to do that, you have to be able to hook the library calls so that I can see when they happen, right? And so that's a defense use of process manipulation, okay? Another time you're going to see pretty extensive process manipulation is in anti-cheat functionality, right? And that's usually if they're back-ported, so somebody makes a game and later on they add the anti-cheat afterwards, but anti-cheat is doing a lot of this type of backdoor activity. And so you can also use this type of stuff to defeat anti-cheat, right? You can pull those hooks out.
So, it's just anti-cheat specific. Hardware spoofing, or is it?
Could you beat it with hardware spoofing? Is that the question?
Like hardware ID spoofing.
Hardware ID spoofing. Well, a lot of anti-cheat is not reliant on hardware, right? There are licensing products that make use of hardware dongles for licensing. And some of those can be beaten like this, but if they do a good job, they use crypto, so I can't, right? But no, generally not. Anti-cheat isn't hardware reliant, so I'm looking at that. All right, so this is the first time that I'm going to go over a bunch of stuff in Windows. So what I'm going to do is talk about how I would do this stuff in Windows, and then we'll talk about how you do it in Linux. In Windows, you are provided syscalls specifically to perform these types of actions. Like they hand that to you, the operating system does. In Linux, you are not handed anything like that. It is assumed that if you want to do something like this and it's legitimate, that you just recompile your code. It's open source. You just change the code. And if you can't change the code, then you shouldn't be doing it. But I suspect a lot of this stuff was added to Windows in the first place specifically for antivirus, right? But it allows you to do some nice things in a much cleaner way than you would have to do it in Linux. So the first thing that you need to do to manipulate a process is have the right privileges. So on Windows, you have a much more complicated privilege situation than you do on Linux in general. On Linux, you've got read, write, and execute for user, group, and everyone, right? It's the same way how that files work. You have the same thing going on with process privilege. On Windows, however, anything that you can do has its own individual privilege that is a set of flags in a token that the kernel holds on to. Okay? So you need to have process read privilege, process write privilege, et cetera, or you just need to have SE debug privilege. Now, by default, not even admin has SE debug privilege on admin services, but admin can always ask for any privilege it wants. So if you are admin, you can ask for SE debug privilege. If you have SE debug privilege, you can do anything you want to any process. Okay?
So in Windows, say admin has access to it, or is it just
No. So on Windows, even admin does not have privilege to do certain things. Only the kernel does. However, because you're admin, you can ask the kernel for anything you want, so you can ask for those privileges. By default, if you tried to attach a debugger to WinLogin, it wouldn't let you do it. But if you were like, give me SE debug privilege on that process, now attach, it would be fine. Right? You just need to know that.
does it check on if you're an admin?
No. There is no such thing as checking it if you are a user in Windows. It checks your token. The token is, the process has a token, and then your token has to be the way you access it. So that's the first thing to know. If you can't attach a debugger to something, you need to make sure the privileges are checked. If you do have the correct privileges, however, you have some quite lovely functionality that makes this very easy. The first one is open process. You give it a set of flags for your access. This is almost always going to be false. This means if you fork off another process, is the process handle that you just get, should that go to that forked process as well? We don't really care about that. And then you give it the process ID, and that's it. And it will hand you back a handle. So a handle is basically the same thing as a file descriptor. We've talked about this before. It is an index into an array, for process array, that stores at the index a pointer to the actual object storing this information in the kernel. And that is how you access kernel objects from user space. Right? So you can think of that as a file descriptor. The same type of file descriptor you've used in all your shell code, like standard in, standard out, standard error. It's one of those. Okay. Next thing you've got is virtual alloc EX. And that allows you, just like mmap, if you looked at mmap when you did your homework, it's the same exact thing, except you have an extra argument here, which is the process ID. So if you have a handle to a process, you can ask for memory to be allocated in that process instead of yourself. So Windows functions tend to have a regular function and then an EX version. The regular function calls the EX version in all cases. The EX version takes more arguments. The regular version makes assumptions about some of the arguments. So if you call the regular version of this, it'll say, give me my process handle, and then it'll call EX with your arguments in your process handle. That's the only difference, right? But in this case, we can pick the process. So once we've opened a handle to another process, we can now provide that to virtual EX. We can give it a page-aligned address. This is just like mmap. We can give it a page-aligned size, right? So units of 1,000 hex. We can decide if it's shared or any other things, and then we want read, write, execute protections, stuff like that, right? So we can open a handle to a process, allocate a bunch of read, write, executable memory in that process, and then we can write to that memory. So we've got a handle to our process. That last function returned us back the address that it mapped for us. So just like mmap, you ask for an address. It'll try to put it there. If something else is there, it'll walk along until it finds a space and tell you what that is. So just like with mmap, don't make the assumption that the address you asked for is the address you got. It's not always going to be the case. This is the buffer in your process to read from, size you want, right? And then this is the output. A lot of the times in Windows APIs, you will have an error code come out of this. So it's either a Boolean or just an integer that's an error code. And so it'll always return you like 0 on success. But you've got arguments that are labeled out here, and you notice it's a pointer. So it'll write basically what the return value of the function is into that. And this allows it to give you a structure back or multiple different returns, things like that, right? So if I'm calling this with a size t local variable, I would use the ampersand to send it as a reference, right? Does that make sense? I want to use load effective address to send the address of the integer I want populated. Okay. So we can open a process. We can allocate memory in the process. We can write to that. And so everything that we need to be able to do to just inject a thread into this sucker, we can do here. And then a little bit later on, I'll show you exactly how we would get code running. But let's look at what you have in Linux to kind of perform parallel functions to this. First off, your privileges for Linux. Just like a file, your process is a user and a group ID, and it's got read, write, execute for user group and all, and those things have to jive up for you to make this function. But once you do, you have kind of 3 ways that you can manipulate memory in a remote process in Linux, provided you have the privileges. So the first one is procfs. If you are running Linux right now and you look in /proc, you'll see that you've got a bunch of processes by process ID and directory structure in there. You have the file maps that you can cat to take a look at what your memory looks like. Let's do this real quick. So you can see what it looks like. All right, so if I cat proc PID maps, and that's the PID of my shell, I see something that you should be fairly familiar with seeing now if you're dumping info proc mapping from GDB. We've got a start address, an end address, the privileges on the page, what's mapped there, right? So all that stuff you can look at from proc. From there, you also have you have access to map file. You have access to mem. So if I want to do that, what do I want? I want access -b1-s. Help me out with the XXD arguments here. Is this right? -L1000, is that going to do it? No, because I didn't put that's not going to do it. No. well, I don't remember my XXD arguments clearly, but that file, procmem, actually contains all of the memory mapping, and you can dump it out by address. You can read to it if you open it as a file. You can write to it if you open it as a file, and you can write to specific offsets. So you can use that to directly manipulate all of the memory in a process. And you can know what you want to manipulate by looking at the map first, right? So you can know where all the pages are and then read right to it. The second way that you can do this is this eye chart. Process virtual memory, read virtual, process virtual memory, write virtual. And this uses IOVs, so input-output vector structures to do that. And so each input-output vector structure defines a page. So it's got an address and a size. And you'll set that and call these functions. And you will have what you want returned back to you in the remote IOV. Right? So depending on whether you're reading or writing, you'll put what you're looking for in the local IOV or what you want to write in the local IOV, and then the remote IOV will be returned back to you. Okay. And so that is basically like write process memory from the Windows side. And then finally, the one that you're probably going to use most because it is the most powerful is the API that GDB itself uses for debugging, which is ptrace. So ptrace is the Windows debugging API, and it all happens through this one function. And the ptrace request op can be peek data, peek user, poke user, get regs, set regs, and quite a few other things. But what that basically means is that you can use this to read arbitrary data. You can use it to write arbitrary data. You can use it to read from registers, and you can use it to write from registers, and anything else that you can do with GDB, you can ask this guy to do. That data is a pointer to a structure of a different type based on what that op is. So it looks a lot like doing an IO control to the kernel, right? Anytime we call this function, it's called with the same arguments, but that data is mapped to or cast to a structure of a type that is specific to the operation that you're performing. Okay. Now, thing to note here: the other two ways that we looked at process manipulation on Linux are only capable of reading and writing memory. This one is capable of reading and writing in memory, reading and writing registers, and anything else that GDB can do. So this is generally the one that gets used, although because the process VM write is a little bit simpler to use than the ptrace poke data, sometimes you'll do most of your work in ptrace, and then you'll use the process VM write just because it's a little bit faster, a little bit easier.
What does the word like poke mean in this context?
So peek and poke are old school computer terms from when you would use I/O pins on a processor. If you mess around with a Raspberry Pi, you've got that header, those pin headers, right? And you can turn on and off LEDs with that thing, right? Peek and poke are what you would say if you were referring to reading from or writing to one of those pins, so like an I/O pin. And so that terminology is carried on here, but it means peek means read and poke means write.
Okay.
I don't know why they don't use it for registers, but use get and set. Okay, so those are our basic APIs that we've got to mess with our processes. And there are kind of two things that you're going to want to do here with that in general. And the first is injecting arbitrary code to run in the process that's kind of independent from what the process is doing, right? So let's say I want to backdoor something. I want to have what we call a persistence mechanism. I've owned a computer, and I want to hide inside a service or a server that runs all the time, like the HTTPD server or something else like that. I don't want to be running my own process that somebody could find in a process list and then have to go and mess with the kernel so that it doesn't show up in process lists. I just want to live inside this server and do my thing. So I would do thread injection, run my own thread. The other thing that you would want to do is either monitor or manipulate what the process itself is doing in its standard functionality. So in this case, I'm primarily concerned with the process.
So in regards to like thread injection, is there like malicious process running alongside the existing process?
Or a malicious thread running inside regular processing. Some of the best ways to do that are to own that service remotely and never touch the disk. Just do all of your work inside the process, right? Then nobody can check for nobody can really look for you very easily. The second thing, if we're concerned with that process in specific and data that it has or how it is reacting to data, then we would want to make changes to that process, and that would involve more simply hooking, okay? So we talked about hooking a couple times in here. All right, so this is your normal function preamble, right? That lives right at the start of the function. And you almost always see something like that. This is only here if you've got local variables, but you almost always do. So that's kind of what our preamble looks like. And then in terms of size, let's see, this is 1 byte. And this is what, 3 bytes. And then this is going to be probably 2 or 3, something like that. What we want to do, we'll get to hooking in a second, but you're going to replace this boop, 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 with a jump. And that jump's going to go to someplace else. And that someplace else could be code that you allocated and mapped, or if you are performing hooking on like a static binary, you can use space that already exists in the code page. So a while ago, I did a patch for Adobe PDF Reader for a bug that they had. And the way that I did that patch is I hooked the malicious function, or not the malicious function, the function with the bug, where the bug was. So I replaced the code that was there with in a hex editor with a jump. And that jump went to some of the space between functions. So generally in a static, or in any binary, the functions are kind of aligned, right? So they're going to start on 0, 0, 0, or the page aligned, which means that if a function ends not at a page end, there's a bunch of space before the next function starts. That space is usually filled with just trap instructions, so CCs. If you're using IDA or Ghidra, it probably doesn't show you those, but it'll say like align parentheses some number. And that means that there's a bunch of garbage there I'm not showing. That garbage is still in a executable page, so you can go write code where that garbage is. And if you don't have enough space in that chunk, you write some of your code there with a jump, a relative jump to the next section of alignment junk, and you write some more code there. and you keep going until you have, written all the code you want. And then at the end, you jump back into the function. So if you are looking at a static binary and you want to modify it, you can make it do whatever you want, provided you have the space in that alignment to write the instructions you want. Right?
Why have that space? Like, why?
There's a couple of reasons. So in a modern context, if you want to use control flow guard and you want your map to be not ginormous, you want to have a very limited number of places where functions are valid. Because if you have every byte be a place where a function is valid, then your map of your bitmap is going to be as many bytes as there are in the program. But if it's aligned, then your bitmap can be much smaller, right? But generally, it's just on for alignment reasons. A lot of compilers do it.
So for like manipulating the X to inject the jump, this is done with a static binary.
You could do it both ways, right? So you can do it in a static binary. If I got the binary on disk, I just edit it. However, if it's in a running program, what you will do is protect the page writable, right? Because right now it's read, execute, and not write. So you protect it writable. You make your changes. You protect it back if you want to be clean about it. You don't have to, though. And then you let the thing run again.
So the process to run multiple times.
Say what?
The process to run.
The process has to run multiple.
Like, so if you're doing you're attacking, it has to run once. You make a change.
No. So give me a second. When we get to the end of the presentation, I'll walk you through all of the steps to hook on a live process. But hooking can be done both on a live process and on a process on disk, is what I'm trying to say. And if you're doing it on disk, you don't necessarily have the ability to allocate memory. So using the space in between functions is a good way to get the space you need to write the instructions you want, right? You can just overwrite the whole thing, but often you don't have space in line. And the instructions you want to add may be larger than the instructions you are replacing, right? Or you may not want to replace any instructions at all. What you may want to do is add some, in which case, in this preamble example specifically, you've gotten rid of all of this stuff, right? So the first thing you need to do, or the last thing you need to do after you run what you want to run, is do the stuff that you got rid of, right? That's one of the primary things you need to understand about hooking. You are replacing instructions with a jump. So you need to do what those instructions did, or else the whole thing's not going to work, right? You can't just trash it. You are now responsible for everything that you overwrote. You got to do it. And depending on what your assembly looks like, you're probably going to have to save off the state of the system so you can restore it again afterwards, right? There are registers that are assumed to be consistent between function calls and registers that are assumed to be trashed by function calls. You need to know what those are and maintain the ones that are assumed to be maintained, right?
So in the preamble jump, are you effectively creating your own stack?
No, you're not creating your own stack, but you are going to act as though you are the function. So you are going to use the stack in the same way the function does. You can think about it as extending the function, basically. Right? You're just adding instructions to the start of another function in this case. Right? Right, so on Windows, thread injection is incredibly simple, right? What you have is, and I'll show it to you actually, we'll walk through the whole thing. Oh, there it is. All right, so this is a program that will load a DLL into another process and then create a thread running, loading that library up. And then that library is free to do whatever it likes. So we open the process, we allocate enough space, we write what we need to write. In this case, because the thread is just going to call load library, all we need is space for the DLL name to be written. So we write that into there. And then we call load library using create remote thread. Now create remote thread is pretty simple. It takes your process handle, it takes the function you're going to call, and then it takes a set of arguments to that function, right, as an array. And so because there's only one argument to load library, it's the path for the DLL. Whatever DLL path we want to load, call load library, that'll get run. Load library on Windows will automatically, when you load this library up, it'll call a main function in the DLL, which is, I don't know why they called it this, DLL main. That was a joke. It'll automatically get run, and that's what's going to be used to set up your globals or set any state that you need to set in the library. But generally, you are not, it's frowned upon to spawn a thread or do a lot from DLL main. So if you wanted to do something useful with this program, you would have a second create remote thread after that thread completes. So after DLL main completes, you would call create remote thread with another exported function that would do everything you wanted it to do, right? And that thread would live indefinitely and do whatever. So in this case, we are reading a DLL from the disk. There are ways to walk around that. Generally, the load library function only reads from disk, but you don't actually have to call load library from disk. You can call pieces of it to load things manually from memory. And so in that more complicated space, we would use write process memory to load our code directly in and then create a thread on it. So with these APIs, you can probably think of how, now that you know how to run shellcode, this is giving you everything that you would do with an exploit, just handing it right over to you, right? So all the stuff that you had to do with your ROP, all the stuff that you had to do to get executable memory, all that stuff you can just do with these APIs, right? You don't have to mess around on Windows. However, on Linux, you have to mess around because you have two problems. First problem is you can't map memory with any of these things, right? So you have to figure out how to map it yourself. The second problem is you don't have create remote thread. So you have to figure out how to kick off a new thread or change what's executing in the moment. And so that is somewhat obnoxious. Let's go over what you actually would have to do. What we do have is all the functionality of the debugger. So we've got a set of steps that we want to perform. And the first one is we want to attach as the debugger using ptrace, and we need to stop the process from running. While the process is running, we can't really mess with it very usefully. So we put in, we halt it in the same way you would with a breakpoint, right? You need to make sure that where you halted that process is not someplace that is non-reentrant. And so we talked a little bit about reentrancy, but I'll go over it again here because it's not immediately obvious what the problems there are. There are library functions that are messing with global variables very often. The most obvious example is your allocator. So if somebody is allocating memory or freeing memory when you have halted the process, you are going to be in trouble because what you are going to do is modify memory, right? So you need to make sure that that's not happening when you halted this process. One good way to do that is to set breaks in the threads in places that you know are reentrant and wait for them to hit. Okay, everything's stopped now. The next thing you need to do is pick a thread you're going to use for this and save off all of its registers, because you are going to use that thread to do something else. And if you want it to continue to run afterwards, you need to save everything off. So you peek all the registers and you save them off in your external program. Okay? Then you write a ROP chain. And you're going to write a ROP chain that does mmap. Okay? And you're going to put that at the very bottom of the stack. So you figure out, you look at the stack map and you say, the current frame ESP is here, but there's like 5 more pages mapped underneath it. This is where you're going to store your ROP chain. Okay? And that ROP chain is going to mmap you read, write, execute pages. Okay? And then, or probably you could just use read, execute pages. I'd have to look at how process virtual memory works and if it respects the protections or not. I don't know if it does. But to be safe, read, write, execute. You move ESP down to the bottom of your stack, and then you move EIP to a ret instruction, and then you run your ROP chain to do the allocation, right? Because you don't have arbitrary code in there to do the mmap for you. You need to ROP it. So you ROP it and you set a break. You jump to a CC there. When the program breaks again on that thread, your debugger will catch it. Okay? Now you've got your pages, and you can take a look at EAX to figure out where they are. And you can use process VM write V to write all of your code that you want to run right now into those pages that you have ROPed. Okay? Your loader code should probably spawn another thread and halt so that you can hand back to your debugger. Then you're going to replace all of the registers that you messed up in the course of your ROP chain with the ones that you saved off. And then you're going to set ESP back to where it was, right? And you'll set EIP back to where it was, and then you'll let the process run. And so now you've done all the things that you could have done with virtual alloc, EX, and create remote thread in Linux. It is complicated, but that doesn't mean that it is harder on Linux to do. Here's how
So is there a reason that Windows just gives you no functions?
Probably for antivirus. Yeah, probably for antivirus. The interesting thing here is that while it looks more complicated to do in Linux, it's not program specific, right? So if you write this once and you get it right, you can use it again forever. Probably, if you went Googling right now, you could find it on GitHub in 5 or 6 different forms, right, as a library.
So if you're attacking a process that has like a fixed number of threads that are managed, if you create a new thread that crash the process,
What's enforcing your thread limit?
like a thread.
You can change it. You can modify the whole process while you're doing this, right? If you're running in a debugger, you can modify the whole process, right? Also, if it knows that it has a fixed thread pool, when it reaches the count of the fixed thread pool, it will not allocate any more threads. So you'll just be one of them.
Right, but when I'm talking about the example that hits, like, say that it hits 10,
Uh-huh.
your thread, your custom thread is 9. That crashed the process.
Depends how the enforcement's being done. Right? Depends. That's something you'll need to be aware of, but that's fairly rare. Fairly rare. You could also just check for that when you halt, right? And then wait for the thread count to drop. You would set a watch point on the thread count, and then as soon as it's modified, that'd be your signal. So while you can probably find boilerplate thread injection for Linux, there are cases where running it would cause the program to explode. Like if you happen to halt in a reentrant situation that's specific to that program, you should be aware of that. But anytime you are doing code injection, you should be testing the hell out of it in all sorts of heavy use situations, right? It's a fairly obnoxious case. One of the bigger problems would be you're going to have to make sure that you pick a thread that actually has enough space below where the stack is being used to put your op chain. So that would be an obnoxious thing that you need to figure out. There are a lot of kind of edge cases on this that will be specific to the program. And so that's fairly common for any thread injection, though. Anytime you're doing process manipulation, you need to be very aware of how a process works underneath. Especially when you're doing hooking, it's very easy to hook a function in kind of a generic fashion and make an assumption about what registers you can change and which ones you can't, and screw it up, or screw up your stack in some way. So you really often need to understand strongly what's going on at the assembly level to hook safely, right? It's very, very easy to sweep yourself. All right, so I talked about this a little bit before. When you are replacing code with a jump that is generally known as a trampoline, probably because you're going to go away and then come back immediately. When you are hooking a function, you don't necessarily need to replace the entire function. You can add instructions, right? So you can jump away, do something, and then jump right back to the beginning, having replaced that code, and have the function run as intended. Or you can completely supplant that function call. You can jump away, do what you want to do, and then call ret. When you call ret, the stack's in the right position, you've replaced that function. It will not be called, it'll go back to the caller, right? So you can entirely rewrite something if you want, completely replace a function. Or you can simply add to it. Now, if you want to just replace an instruction and it is an external, replace a function and it's an external function, you might be better off using LD preload on Linux to do that. Because of the way that loading works in Linux being different than Windows, you can replace a loaded function with a function from another library very easily. So in Windows, when you load from a library, it is loaded from a specific library. So if I want to run memcopy from ntdll, that's different than memcopy from bobsdll.dll, right? And so the loader could load you up both of those, and you can resolve both of those differently. On Linux, you've got a set of shared libraries to load, and then a set of functions to resolve. And the load order tells you greedily, okay, whichever one in this load order has memcopy first, that's the memcopy I'm going to call. LD preload will put something at the top of that stack. So you can say LD preload Bob's DLL. And even if you have libc loaded, it'll run Bob's DLL memcopy and not libc memcopy, right? Now, that's only useful if we want to completely replace the function, not if we want to add something to it. And it is more useful in situations where you have control of the program, like you get to call it yourself. That's not going to work in a case where you want to augment somebody's software that's been running after you owned the system. But it would be useful for the fuzzing case that we discussed. It's useful for heap debugging in a lot of cases. So I'm fairly certain that's how Valgrind and most other heap debugging systems work on Linux. But you don't actually have that in Windows, although you do have the search path for DLLs in Windows, which is kind of funny. The way that DLL loading works in Windows is that there's no absolute path provided. It's just the name of the DLL, and it will walk a set of load paths to look for that DLL in order, and it'll select the first one it gets. So if you've got a DLL that lives in Windows System 32, and you got the same name DLL that lives in the home directory, the working directory of the process, it'll preferentially load the DLL out of the working directory instead of the one in System 32. This is a fairly common vulnerability in a lot of Windows software. Let's say you have a corporate laptop that has some AV software installed that stops you from doing something you want to do, and it has kind of permissive library pathing. You can drop your own DLL into the working directory of the antivirus if you have access to that, and it will load up that DLL when you start up the computer instead of the other one, and then the AV software does whatever the F you want it to instead of what your corporate overlords want it to do. Right, so
is the reason that it prioritizes working directory over System 32 is that it's
no, that's just how God wants it, man.
How are we supposed to replace the first two instructions of a function if they're not writable?
You have to make them writable first. You have to protect them, right? So the assumption here is that you either own the process, so you've got arbitrary execution in a process already, and now you're going to make changes to it, or you have privilege to attach to that process. So you've gotten privileges from some other nefarious means, and this is a post-exploitation technique, right? This is not something that you would do to gain privilege. This is something you do with your privilege, right? Process manipulation is post-exploitation activity, not exploitation activity. Make sense? But that's, yeah, one of the things you'll need to do. So when you're running virtual alloc EX, you're going to give it the protections you need to execute there. And then once you have a thread that's executing, that thread will go through and protect the pages that you want to change, make the code changes to jump from where the code is into the pages that you executed or that you mapped, and then you'll remap them, right? So you have to manually change the page protections to make those changes, right? You don't necessarily need to change them back. You could leave it all writable, but it's cleaner if you make it writable, you protect it, you make your changes, you protect it again, back to executable. Right? If you don't do that, if somebody dumps the pages out, a mapping like we looked at in, just like when you ran mprotect on the stack and you had one entry for the stack, when you ran mprotect, now you have two entries for the stack, one of them is executable, one of them is not. Your code page mappings will be like read execute, read execute, read execute, read write execute, read execute, read execute, read, like that. And so instead of having one entry for your library, you'll have like 50 in the mappings, and that'll be fairly obvious. So you kind of want to mprotect them back so they look normal again, right? Even without messing with a process, if I'm an AV and I know something about what the process's pages are supposed to look like, like I'm assuming there's no JIT in the thing, it would be very easy externally to determine somebody had messed with the thing if there were just a bunch of read, write, execute pages in it, So sometimes you're racing scanners, There are several circumstances where manipulating code pages is sometimes a race against a scanner. What is the name of the Windows kernel protection obfuscated thing? Help me out. Well, anyway, I don't remember what it's called, but there is a obfuscated thread in the Windows kernel that does a lot of scanning for weird shit. So it'll be like, did you turn off?
AMSI?
Say what?
AMSI?
No. That's scanning text input to PowerShell. This thing is scanning kernel memory and control registers on the processors to make sure that they are in the way that it previously set them. And it scans like it's some random amount of time, 20 minutes. So it's very rare. Patch guard, that's what I'm looking for. Patch guard. So one of the things you'll do in the kernel is mess with the control register to allow you to execute code from user space, which is generally turned off by a flag in the control register. So what you kind of want to do is turn it off, run your code in user space, push yourself back into the kernel, and then turn it back on again, and try to beat patch guard from scanning, right? So a scanning race. But that'll happen in user space too if you've got some AB or something else that's periodically looking at page mappings.
Yeah, I know like a lot of the old silly stuff, like unlinking your process from the process list doesn't really work anymore because of patch guard and stuff.
I don't think they're changing patch guard anymore. There were a couple of years where every couple of updates they'd make a significant change to patch guard. I doubt that's happening anymore. It was very expensive to maintain something that does weird stuff that's extremely obfuscated in the kernel at a low level. Like, that's probably like 3 or 4 real smart people. And like, there's a limit on how long that exists, right? It's expensive. At Immunity, there was a guy that did the full reversing of patch guard, must have been like 2010 or 2012. And that was a huge pain in the butt. And we were like, oh man, yeah, there's no way they're going to maintain this over time. So I would expect that if you were to do a quick patch guard reverse now, it's probably been the same for almost 10 years. That'd be my guess. But honestly, it's very rare that you're caught by it, just because it's scanning in 20-minute increments, right?
Oh, in 20 minutes.
Something like that. It's like a slightly randomized amount of time around 20 minutes. So usually if you change the control register, do something and change it right back as quickly as possible, you're fine.
Unless you have terrible luck, yeah.
Unless you have very terrible luck. Yeah, and one thing that you should do if you're writing professional post-exploitation mess around code or just exploit in general is run your code 100,000 times. I think Alex Soderov is the one that really pioneered very serious and rigorous testing on these sorts of things. And he would put out reports where you would have a low probability heap exploit on a browser, and he'd be like, for this many tabs open with this average memory usage, here's my graph of running it 100,000 times, and here's where it falls down. And so you actually really have a very good idea of like, if I profile this real fast and it's looking good, then I can do this and get 99% likelihood of accuracy. And that's kind of where you want to be, right? If you've spent 8 months working on a bug, you don't want to kill it accidentally. So doing the last 2 weeks of testing work on your 8 months of work is very smart. Okay. But for most things, you're fairly safe with hooking just because a lot of software is performing hooks all of the time anyway. And so unless someone is being very strict, they're not going to catch you or bother you, because generally what will happen is if someone is being very strict, 4 of the pieces of software that the corporation decided that is necessary for your daily work doesn't function anymore. And so, that just goes off the table instantaneously, right? The very first time a piece of defense software breaks something that somebody needs to make money, that defense software no longer exists, right? Like, does anybody see what happened to CrowdStrike a couple months ago? A lot of people yanked that stuff out instantaneously over that, right? There's a lot of clients that no longer exist for that company anymore because of one misstep, right? Getting owned doesn't actually cost you very much. Having a vulnerability in your software doesn't actually cost you very much. Not in stock price or actual cost. It's like cost of doing business. It's like what Walmart expects to lose in stolen goods. But not having your accountants be able to use their accountancy software every goddamn second of every day, 24/7, that is not acceptable. So that comes first. What was I saying before you asked that question? Something else about why you're generally not caught hooking things. Sure, it'll come to me later.
Maybe the antivirus is doing it anyways.
Yeah, antivirus is doing it constantly, but this is what it was. Anomaly detection in general seems like it's a good defensive idea. You profile what something is likely to do, and then if it breaks that, then you kill it, right? That's actually extremely difficult to do for a number of reasons. And it's the same as the SE Linux problem, where if you haven't profiled what this thing is doing fully and completely in all scenarios that you can possibly imagine, then your profile is going to be wrong and you're going to kill it in legitimate business use, and that's not allowed. And so even for things that we know about, let's say you wanted to profile WinLogin to make sure that it's not calling out to a web server, which it probably shouldn't do, right? Well, okay, maybe there's a PAM module that does work over 888, right? And now you've just knocked out an entire company, right? So in order to do this, what you have to do is take telemetry from every single one of your clients over a long period of time and pull it into the cloud and analyze it and then put together your profiles. First off, a lot of companies that rely on your software are just not going to push stuff to your cloud. So those ones, the ones that are most important to you, you're not going to have their data. Secondly, that's extremely expensive. It's expensive in processing power on all the machines. It's expensive in network traffic to push the stuff up to your cloud. It's expensive in storage, and it's expensive in processing it once it's there. So almost nobody is using SE Linux type things. And even in the most general case for anomalies, you can think you have found an anomaly, and when you go looking for it and testing this check, you will find it literally everywhere. Anything that malicious software does is done by regular software. Software is Turing complete. It is very difficult to say with certainty that something is malicious and not have 50 normal programs do it. When I was working at SourceFire, there was a new library that had come out for JavaScript obfuscation. And we could profile this thing and say, if the file comes across the network and it's using this obfuscation method, it's got to be malware, because all the malware is doing this obfuscation, so we can't check to see if the JavaScript is doing something malicious, right? So we write the thing and we send it up, and then it kills all of Google Maps because Google did not want anyone to know how their mapping JavaScript works, so they were using the same malicious obfuscation in Google Maps. And so we had to take it down. And that happens every time in my career I've ever tried to do that kind of anomaly detection. You think you've got it, you put it out there, or you start using it and you find that 50 legitimate things do the same thing. So in practice, it's very, very difficult to catch someone at shenanigans on the computer. Right? And that's why most anti-cheat is doing the dumbest things that you could possibly imagine. Anybody hear about the person who had that quote-unquote exploit in Call of Duty where they were getting people banned? Do you guys know how that worked? The exploit worked? One of you say it.
Just type it in the chat.
No, the chat.
Yeah. The thing is scanning for the string, which is the name of the cheating program. It is just scanning memory pages for the string I'm cheating.exe or whatever that. And so what this dude did is he wrote a Python script that would connect to the servers just well enough to be able to do text chat, and then he would send that string. And it would be in their memory pages, and they weren't looking for it to be in executable pages, like a sane person would do. They were looking at all the pages. So even if it's just in a read-write text buffer, it's still got these people banned, right? And that's what they all do. It is the dumbest possible thing, right? I know Jeremy went to great lengths to defeat an antivirus with a kernel driver, filter driver, so that when it looked at the drive, it wasn't seeing the malicious software. Okay, well, here's how antivirus works. You have those code pages, right? Those are the read executable code pages. It SHA-256s those code pages. That's a checksum. If the checksum matches something in its list, that's bad. Okay, well, we already discussed that between functions, I'm going to use a marker that works for your benefit and mine. Between functions, you have alignment bytes that are all just CCs that are never called and never used, right? So if you write a Python program that loads up your malware, and it goes with a disassembler and it finds where all the alignment bytes are, and it finds how big they are, and then it randomizes the alignment bytes, and then it writes it to disk and it pumps it out, and it does that every single time you infect somebody, well, the SHA-256 is different for every single one of those, right? So you just invented your own genius polymorphic malware, which you didn't have to do anything clever at all. You wrote like a 3-line Python script, and you've just beaten every single antivirus. So you don't have to like shoot a space laser at the moon to defeat these things. You just have to understand what they're doing and like leap over a little fence. Right?
I like my space laser though.
It was a great space laser. You did a good job. It's worth learning to space laser. You just want to point it at the right stuff.
So the antivirus checks like the pages or the bytes?
The bytes in the pages,
Okay.
right?
So
It's a string of bytes. It's going to check some of those. Is the homework up now?
What home?
Homework 4?
Not yet. I have to make it into a little fill in the blank.
Okay, all right. So we're going to have homework 4 up. It is a small report. What do we want to do? Do we want to have everybody put in their a copy of it? So you will make them as a team. Do you want one per team, or is it easier if we have everybody put in a copy?
Everyone should put it.
Okay. So your team is going to make one report together, but you're all going to submit it. Clear? Everyone's going to submit one. Cool.
Because if we see someone missing, that's bad.
You're never going to be able to get that together.
Can you just do a group submission? Like adding, like,
group?
in one submission, but like adding.
Oh, you could do that, yeah. You could do that. Make a group submission.
You can add like group members on
We
grades.
also want to make sure everyone's doing something though.
That's true.
Well, so part of the report is who are the members of your team and what are their initial tasks. I provided a set of reasonable initial tasks. And so if there's somebody on your team that does not have an initial task assigned to them, 1, that'll be a problem. And then 2, when we look at the project at the end, I will know who was responsible for which part of the project. In your final report, you're going to need to list Bob is responsible for VM setup. Jane is responsible for building the debugger. So-and-so is responsible for setting up AFL. So I'll know who did what in the project, right? That's going to be a necessary part of this. And you'll be responsible for the portion of the final project report that is assigned to those things you did. So if you have 1 rock star in your group and 4 dead weights, it's going to be extremely obvious because the 1 rock star section is going to be like 5 pages long and the 4 dead weights are going to have a paragraph in what they did, right? or there will be more entries and tasks for one person than others. So that's what we're looking for here. Please put those 3 hours per week for the duration of this homework into working your final project. If you need help with the final project, reach out early. Do not reach out